I now move on to a different application area, which is now moving away from nanomaterials to looking at bulk materials and how Raman can be used to investigate the change in material properties through a function of depth through the sample. So for many applications in material science, you have multiple layers. So some examples are protective coatings in industry, typically composed of several layers, or you might want to look at how the properties of a single material change as a function of depth, for example, looking at degradation and permeation through a substrate. Many polymers that are deposited as laminates, so one polymer deposited on top of the other to get a combination of their properties. And also in semiconductor manufacturing, you very always have a stack of different materials, one atop the other. So we would like to use Raman microscopy to image how these properties change as a function of depth or identify different properties at different locations through the sample. And this is something we can do using Confocal Raman. But we have some challenges to overcome to do it. So the main challenge to get any information along this depth or z-axis, as it's more commonly called, is that when you excite the sample, so if you put the objective lens is up here, the laser's coming in, and you get this three-dimensional excitation volume. So your laser is effectively exciting at every point along the z-axis. And as a result of this, if you were simply to try and measure the Raman spectrum as a function of z, you would have a very blurred image, as you would have out of focus contributions from every possible z value here because the laser is exciting the entire volume. To show this on a different picture, so this is the same principle, but now looking at a 2D projection onto the sample. So the green here shows this excitation volume that I was talking about, where this is our z-axis. And if you've got Raman scatter originating above the focal plane, so the focal plane is marked here with the dashed white line. If you've got Raman scattering originating from above, this is collected by the objective and is focused and reaches the detector. The Raman scatter from below the focal plane also reaches the detector and the focal plane. So you collect from the entire excitation volume and you can get no depth information. And the solution to this is to introduce the confocal pinhole that I showed on one of the first slides. And the idea of the confocal pinhole is to give you this depth resolution. So if we have Raman scatter originating from above the focal plane, this is now blocked by the pinhole from progressing further. The same when it originates from below, and it's only Raman scatter that originates at the focal plane or very close to it that is focused through the pinhole and can reach the detector. So the pinhole blocks the out of focus Raman scatter from reaching the detector and improves the axial resolution. And I should mention here also that you sometimes see, if you're looking at Raman microscopes, the terms truly confocal and pseudo-confocal. And the RMS 1000 and the RM5 are both truly confocal microscopes. And what this means is there's a physical pinhole in the confocal plane of the microscope. And this gives you optimum spatial resolution. Some microscopes are known as pseudo-confocal, which simulate this pinhole using a combination of their spectrograph entrance slit and their CCD detection region. But this does not result in the optimum spatial resolution that you can achieve by using a true pinhole. Another important parameter of the pinhole is its size. It's not good enough just to have a single pinhole, as if the pinhole is too wide, the out of focus scatter can still enter the spectrograph and be detected. And you might then ask then why do we not always just use a very narrow pinhole? And the reason is that this reduces the throughput of the Raman scatter through your instrument and would lower the intensity. So if you've got a wide pinhole, you have much higher throughput, higher intensity, so you can acquire in a shorter amount of time. If you've got a narrow pinhole, you've got better axial resolution, but you reduce the throughput. And you really want a way to balance these two depending on your application. And the RM5 and the RMS1000 both have adjustable pinholes that can be changed from 25 microns to 2 millimeters, depending on how much confocality is required for your application. So you can change from a high confocality, low throughput mode to a non-confocal, high throughput mode. And for those of you listening who might have no interest in looking at depth profiling or samples with multiple layers, the confocal pinhole also has other benefits beyond just the axial resolution. So it also includes the lateral resolution of the microscope, so the XY resolution, and more importantly, it improves the image contrast. So in Raman and photoluminescence microscopy, you typically have a lot of background light. So in Raman, background fluorescence, and in photoluminescence, you have background scattering. And by narrowing the pinhole width, you remove this background and improve the contrast of your Raman and photoluminescence images. An example of how the confocal pinhole can be used in practice is looking at multi-layer polymers. So here we have a PET-PVC-PET polymer stack, where PET and PVC are two types of commonly used polymer. And here they've been incorporated into a laminated structure with multiple layers. And we can use Raman microscopy to profile through these layers. And if we didn't know the plastics, we could identify which plastic was in each layer. An example of these Raman depth profiles are shown here. So I'll just take a couple of minutes here to explain what's shown here. So the x-axis here is still the Raman shift, as you show in any Raman spectrum. But instead of showing the Raman spectrum as an intensity profile with lines, the spectral positions are instead shown by color. So where we have bright color here means you've got a strong Raman peak. And the y-axis of this plot is now the Z depth through the sample. So this is a function of depth in micrometers through this PET-PVC polymer stack. And you can see that the Raman spectrum changes when you have PET. You've got peaks here, and the PVC has additional Raman peaks around the 600 to 800 region. And so you can see that there's multiple layers in this material, and you could import these into an analytics program if you didn't know what the material were, to identify the composition of this layer, the different layers. And you can also see here that there's two different images. So one of these was measured with a 100 micron pinhole and the other with a 25. So if we look at the 100 first, you can see that the Raman peaks are blurring between the different layers. So the PET peaks around 1400 are blurring into the PVC. But if we move to a 25 micron pinhole, which has superior axial resolution, you can see there's much clearer discrimination between the layers. And this is an example of how you can adjust the pinhole width in order to get the desired axial resolution for your measurement.